Hello, this is Engineering 201, EGR 201, Electrical Fundamentals, first term of Electrical Fundamentals, and we'll get started with some introductions. The the class is at Chemeketa Community College. I'm Mark Miller. I'm an instructor of engineering there, and you've got my contact information here. There's my phone number. There's my email. A lot easier, probably better to contact me by email than trying to catch me on the phone. This website here, if you're interested in getting advice on studying engineering and whatnot, that is one possibility. Most of you are probably well past that. And another website that's probably better for you is my personal website here, where I put the class materials, and you can have links to these videos and so forth. So I assume you've got the pause button and the zoom and whatnot, so I'll flip the page here. When you use that link, you'll go to, like I said, my website, and you can come over here and click on Engineering 201, and you'll find the weekly videos and homework and that kind of stuff. Also, there's a sub-page under there for the labs and that kind of thing. A couple other areas that you may want to keep in mind is advising. There's information for classes, advising, things like that. And also I put some various things under this and that. So a few things to keep track of as you go to that site and go through the class. Well, speaking of advising, I talked about this in the statics class, and I don't want to rehash everything, but I also realize there's a lot of people that aren't taking that class, so I'm going to hit some of the high points. If you've sent me an email or you've sat down with me during office hours for advising, or if you go to the website under the advising tab, you can get this advising document. It's a multi-page document that has information on classes that you can take and go to Portland State or Oregon State, Oregon Tech, or those things. So I encourage you to download that and look over that. I do want to quickly spend a few moments talking about the classes that you should be in. Again, I'm going to paint with a pretty broad brush here. The majority certainly are looking at Oregon State, and probably civil, electrical and computer, or mechanical. If you're not going to Oregon State, that's not a problem. You may well still need electrical fundamentals. And if you're not in one of these disciplines, you're in some other discipline, that's okay too. But I think the vast majority of students fall into this, what I call the big three: civil, electrical, or mechanical. So we look at the first year and then the second year. So this is where you are, fall term, your second year. And if we look at this, you should be in Physics 211. Be real careful with that. Do not mess around with Physics 201. That's not going to work for you. So Physics 211, the calculus-based physics. Then Math 254, and then EGR 201, this class. That'll be the most fun. And then you're going to be in civil mechanicals, or in what? EGR 211, statics. And if you're an electrical, what are you doing if you're electrical? Instead of taking statics, you're probably doing the CS 161. Okay. Now, I think you'll see with this note here that if you've got the time and can put it into taking 211 as an electrical engineer, that might pay off in the future. I think it's some good skills to have and a good way of thinking. But strictly speaking, the civils and mechanicals will be in statics. The electricals will be in CS 161. You're looking at 4 classes with physics, math, engineering, and then either the statics or the CS class. So make sure that you're in those classes. This class is only taught, I believe, once a year. Physics is only taught once a year. This class is only taught once a year. So if you miss the boat on this deal, you've got problems. So I just wanted to spend a little bit of time making sure that everyone was in the right class. If you've got questions on this, catch me during lab time or during my office hours or something like that. So we'll move on to the heart of the class then. So when we talk about EGR 201. Sometimes this class gets a bad rap, electrical fundamentals. People sometimes will struggle with that, and I would suggest the way to tackle this class is to read chapters 1 and 2 in your textbook. And that's a little bit like riding a bike. You can read about riding a bike all you want, but sooner or later you have to get up on it and you have to tackle it, and sometimes you get scraped up and whatnot, but you got to sit down and work some problems. So when you go to the website and you download the document for week 1, it not only has a link to the video that you're watching, it will give you these PDFs that I'm making. You notice that I'm numbering the pages here, so I'm going to make a PDF out of these. I would probably recommend, as you watch the videos, downloading the PDF first, and then you can write on that as you watch the video. But you'll do what's best for you. Maybe just reading the textbook is fine. It's up to you. But and I was not a big reader going through school, but I think even if you're not used to reading the textbook, I would still really encourage you to read chapter 1 and 2 of the textbook. It's really foundational. And then work some problems, and then go back and reread chapters 1 and 2. And you have the luxury of this class being videotaped, that you can also go back and look at the lectures. You're obviously not going to want to listen to me again and again talking about reading chapters 1 and 2, but when we start working problems with difficult concepts, you want to go back and look at those and rewind it and look at it and stop it and try it yourself and so forth. So this just keeps repeating itself. You want to read chapters 1 and 2, work some problems, read chapters 1 and 2, and really build this foundation. I would encourage you to spend a lot of time on this class at the beginning to really make sure that you have a strong foundation. And I think that will pay off big. So there's a tip there. Hopefully that pays off. Usually there's a lot of frustration. The light bulbs don't come on for a while, and then the light bulbs start to come on, and people realize it's not as hard oftentimes as they've made it out to be, and the class goes pretty well. So really dig in hard here at the beginning. That's my encouragement and my piece of advice on this. Well, speaking of the beginning, let's start some basic definitions here as we start to study electrical fundamentals. An electric circuit, I guess we should define that. An electric circuit is an interconnection of electric components. So we have an electric circuit as an interconnection of electric components in a closed path. Probably closed path is the most important part here. Always use an example here. It's easy to draw. We'll take a couple of D cells and make ourselves a flashlight. Maybe we'll use 3D cells, make a real fancy one. I was drawing this one time, and the student said, "Oh, it's illegal to have more than two cells in a flashlight because it gets too long. It can be used as a weapon." That's why the police have them. And I thought it's kind of odd what ideas that people come up with. Really, anything could be used as a weapon. But anyway, so we got 3 batteries here. I'm not sure whether this is legal or not. I think it's quite legal, but use this at your own risk. So we'll put the bulb up here. There's the light bulb with the filament. Okay, so is that a electric circuit? Well, it's certainly not an operating electric circuit because we have a path for something to flow through here, and we're going to talk eventually about what that is. That's positive things or negative things, and it could flow up here, but then there's no return path, is there? So we probably need something like this, a return path for that to go around. So it's very important that it is a closed path. Then we always get the philosophy student that talks about, well, there's a switch. If the switch is open as an electric circuit, well, it's certainly not an operating electric circuit, is it? So the most important part is closed path. You have to have a path for return. I've seen people in automotive wiring. They really do a very good job of wiring on this part of it, and then they ignore the ground path, and sometimes the ground path, the ground wire, may be glowing red hot. So sometimes this path is a little hard to find. If you have a metal body flashlight, you may not necessarily see that. They're probably using the body of the flashlight itself for that. If you have a marker light in the fender of your car, you pull it out and it probably just has one wire going to it if it's just a single marker light. And you might wonder, well, is that some weird phenomena they're using? Well, no, they're using the fender, the metal fender, the chassis itself, as this return path. So something to keep an eye on. You need to make sure that you have a way for it to flow around. It has to, whether we're thinking about electrons flowing or positive things or little rubber balls flowing around, it needs to have a way to come back. Let's move on and talk then about electric charge. So if we have an electric charge, we could talk about the charge in an electron, E minus, I think is what probably you've used in science to indicate an electron. I'll stick with that. We won't be using it very much. But the charge on an electron is 1.602 times 10 to the minus 19. And we're going to use coulombs. Okay, the most elementary unit of charge would be the charge on an electron, and we're going to group that up into coulombs because, quite frankly, the charge on one electron, we can't do a lot with that. In engineering, we can't light lights and turn motors and things like that. Now, if you invert this, we can come up with 6.24 times 10 to the 18 electrons per coulomb. Okay, and I encourage you when you write coulombs not to abbreviate it as C. If I'm going to abbreviate it, I'll use COUL. We're going to use C for capacitance later on. We don't want to confuse that. So what we've done here is a little bit like money. If we go down to buy a car, purchasing the car in pennies is probably not a very good way to go. Trying to light a light with electrons is not a very good way to go. So we group up a bunch of those. We group up a bunch of pennies into $1, or if we're going to buy a car, maybe we'd have to then group a bunch of those dollars into $1,000 and call it $1,000 or something like that. We do the same here. We group up the electrons. We group up, in fact, 6.24 times 10 to the 18 of them. There's a lot of them there, and we call that a coulomb. And then a coulomb is an amount of charge, a unit of charge that we can really do something with, and we'll define ampere based on that and so forth. So we won't be working too much with the individual electron, but we will be working a lot with the coulombs. So, well, moving on then. Let's define a couple quantities that always get kind of confusing. And that is, this next one goes by several different names. We might call it electromotive force. Or we call it a potential difference. Or maybe we'd call it a voltage. Or we could even call it a voltage difference. Okay, and all of these are really a definition of the work done in moving the unit charge. Work done in moving the unit charge. Now, probably, I'm not going to use the term electromotive force too much. They'll use that probably a lot in the sciences, physics and whatnot. You'll probably use electromotive force. I'm probably going to use these three quite a bit. But I might talk about potential difference, difference in potential, talk about voltage difference. I'm going to use those fairly interchangeably, and I'm going to use the symbol V for that. Okay. V for voltage. Now sometimes people will use electromotive force and they will use the symbol E. And I don't want to spoil any fun here, but probably if you look at Ohm's law, V is equal to IR. Some of you maybe have seen this written as E is equal to IR. Or I is current and R is resistance. But we use these V and E interchangeably. So if someone comes along and starts talking about E, think back and, oh, I bet that's voltage or potential difference. So work done in moving the unit charge. Let's look at that in a little different sense. So we could say that 1 volt is equal to work per unit charge. So further, we could say that let's see, work is what? A Newton meter? Would that be work? Okay, so we'll say that we have 1 Newton meter per, what's the unit charge? Coulomb, right? Okay. Coulomb. So we've got a Newton meter per Coulomb. Let's see, a Newton meter is actually a joule, isn't it? So we could say that this is a joule per Coulomb. Okay. So actually a volt then is a joule per Coulomb. So you go down to the auto parts store and say it's like a 12 joule per Coulomb battery or a 12 joule per Coulomb rated light. They'd probably throw you out, but technically you would be correct. So the base units on a volt is a joule per Coulomb. Now got a little space here. I'll try and add on this one sheet, because I'd like to, as they say in English, compare and contrast these next two. And this next one is an electric current. Okay, an electric current is time rate of change of charge. Okay, time rate of change of charge. So we could say then that 1 amp, that's our unit for electric current, or an ampere, is equal to the time rate of change of charge. Well, the charge, that's a Coulomb. Coulomb per time, let's see, we'll say time is in seconds. So an amp is a Coulomb per second. So when you say you have 100 amps flowing, that's 100 coulombs per second passing a particular point. Okay. Now, I've got these two here. We want to think of this in a garden hose analogy, if you will. Maybe you've heard this before. We think of this as a difference, as a pressure, and this as a flow. So can we have pressure without flow? Absolutely. If you look at the faucet in a kitchen or something like that, you have pressure behind that faucet without flow. It's not until you open the valve that you actually have flow. So you can have pressure without flow. If you look at the plug-in on a wall, you have pressure without flow. You don't have flow until you plug something into that receptacle or outlet. So it's very important for us to think of the voltage or the electromotive force as pressure. It's important to think of current as flow. And I'll be probably kind of correcting you when you're talking to me in lab and talk about the voltage flowing through something. Oh, no. Voltage doesn't flow through something. Voltage is a difference. It's a pressure. It's across something. And if someone says, well, we need to measure the current going across that. No, current doesn't go across something. Current goes through something. So it's very important to think of current as flow and voltage or electromotive force as pressure. And that's where we get the garden hose analogy on this. Well, let me put these together here then. We're a long ways from done with electromotive force or voltage and current. But let's take these two. Let's talk about power. We'll look at Watt's law, where power is equal to current I. We give the symbol I to this. Okay, we give the symbol V to voltage. We're going to give the symbol I to current. So power is equal to, this is power, is equal to current times voltage. Now if I look at this from a units standpoint or units analysis, what do we have? We have that current, going back here, that's a coulomb per second, right? Times voltage. What's voltage? That's a joule per coulomb. So we get a coulomb per, or the coulombs cancel, and we get a joule per second. What's a joule per second? Well, that is, of course, a watt, isn't it? Okay. So that's how that works together with power. So that's our unit, is so many watts. And you've probably seen these. You've certainly seen someone talk about a 120 volt device, or a 12 volt device, or something that draws 3 amps, or something that draws 2 amps, or something that's 1500 watts, or 120 watts, or something like that. So you've all probably heard of these things. We want to talk about how they fit together. And again, for clarity here, we use the symbol P usually for this. Well, we haven't talked much about whether we're talking about AC or DC. We're going to start talking a lot about DC, and the next term we'll talk about AC, but much of this remains the same for either of those. And we haven't talked about how this relates to electrical safety. So that'll be a good spot to start next time at the first lecture. I don't want to get too crazy here. We'll leave this as a good starting point. We'll come back and recap this when we start up with the next lecture. So thank you for watching, and take care till then.